Welcome to today's session. Now it is tempting and so easy to just sit back and watch me do some problems, but really you learn very little by doing that. I've been there. I have done that exact thing where I just sat back and watched someone else do the problems, and then I thought to myself, yeah, I could do that. That sounds about right. Yeah, just follow along with what they said. And then the test came and I couldn't do it because that is not how you should be studying unless you are very skilled. For most of us, that's just not going to work. Ultimately, you have to get out a pencil and do some stuff, but that is your responsibility to know, not mine. It's up to you. We've done some of these in the rational function transformation problem set. I think we've done number 3 and we did number 8. Let's see what else is here that is interesting. Let's maybe do, I want to do 2 of them. Why not number 1? There's nothing wrong with number 1. Number 1 is a good question. So problem 111, number 1. What is it? I don't remember. X over 3x minus 6. X over 3x minus 6. All right, so now we see that there are x's in the numerator, which means I am not able to clearly see all the transformations that are in this rational function. That's okay. I just need to do some long division to pull this apart and really see how this function is constructed with transformations of the basic rational function. So let's do long division over here. And let's not. Just planning my space. Let's do it over here. It's fine. Numerator inside the house. Denominator outside the house. Now I compare leading terms. 3x goes into x 1/3 of a time, or x divided by 3x. 1/3 times all of this will be x minus 2. I take that away. X minus x. By design, this is going to cancel the leading terms. Nothing plus 2 is 2. I cannot divide 3x into 2. It's the 2 has a smaller degree than x. So that is my remainder. So that means that this can be written as 1/3 plus 2 over 3x minus 6. Just like I would do long division with just numbers. Now I want to maybe shuffle this around a little bit, make it look a little bit cleaner because I don't like the 3x here. What I can do is, first of all, I'll put the 1/3 at the end because that's my cue I do at the end, right? My vertical shift. I like to do that last. I can factor out a 3 like so. And then I'm going to merge the 3 with the 2 to have 2/3 in the numerator, x minus 2 in the bottom, and a 1/3 extra. Now I see what the transformations are. And I can make my sequence of transformations. So here is my sequence of transformations. And in the interest of saving time, I'm not going to graph these. Once you have the sequence, graphing it should be the most straightforward part, but let me know if it isn't. The fractions are unfortunate, but it doesn't really matter. So, of course, I start with my basic rational function. That was supposed to be a 1. It wasn't supposed to be this curvy. 1. Then I will go to stretching it, of the graph, multiplying the right-hand side by 2/3, which I can put at the top. Then I will replace x with x minus 2. And lastly, I will take the right-hand side, squeeze it in here, and add a third. So we'll just write underneath what happens to the graph, and I'll leave it to you to actually do it. It's just very time consuming, and we can get more problems in if we skip it. So this first one, or multiplying the right-hand side with a number, 2/3 in this case, is a vertical compression. Then replacing x with x minus 2 is a horizontal shift to the right by 2 units. Then adding a third is to the right hand side is a vertical shift up by 1/3 of a unit. And there we go. Of course, you have to be able to do the graph. Sometimes a question is just going to ask you, what is the sequence of function transformations? Then you can stop there. And sometimes it's going to ask you to graph each one to find the graph of the given function. And then we have to just start with the basic one and slowly shift it around and flip it and do whatever you need to do. But I hope that's not the challenging portion here. The long division and maybe the rewrite to really isolate the transformations, that might be the problematic area. And again, don't wait for me to stop and ask, are there any questions? Just interrupt whenever you feel like it. Oh, let's do at least one more of those. What's the hardest one here? I do want to do number 7. I do want to do number 7. Yeah, sure. I'm not saying it's the hardest one, but I don't want to miss it. 111, number 7. Or if you have a preference of which one we should do, we could certainly do that. No one is really saying anything, so I just continue. Number 7, h of x. Just going down the alphabet here. Negative 2x plus 1 over x. All right. I see x is in the top, so I can't identify the transformation. This doesn't even look like it has any transformations. Now this one is easier in terms of the long division because the denominator is only a single term. I don't really have to go through the whole song and dance of long division. I can just separate it over that denominator. Oopsie. Because it has a single term, just an x. And then I can see, oh, the first one simplifies to negative 2 and a 1 over x. Or I can even write it in the very clear form. And then I see, wow, actually there was only one sequence, one transformation. Wow. That did not look like it in its original form at all. Oops, I'll start with y equals 1 over x. And I'll go to y equals 1 over x minus 2. Super simple. I'm not using long division because I don't need to. But if you insist, we can totally do long division inside the house, outside the house. Long division says, compare the leading terms. Negative 2x divided by x, negative 2. Negative 2 then times the divisor, which is just x, is negative 2x, which I take away. Negative 2x minus negative 2x is nothing. The 1 comes down. That's my remainder. It's exactly the same as this version, right? Long division is important when the denominator as multiple terms, then there's really nothing I can do. Well, that's not true, but nothing we can do right now. But when there's just an x, it's much simpler in that I can just split up the fractions and simplify them that way. Rare, but when I see that opportunity to avoid long division, why not take it? But of course, long division is the more comprehensive tool that will, of course, handle this as well. So here I see the only transformation that happened is a vertical shift down by 2. Super simple to draw, I hope. Make sure you can actually do it, right? I'm just trying to save time. Drawing is time consuming and sometimes tedious, especially when I have fractions. This one's easy. All right, let's see if there's another one here that is actually different and weird. Maybe 2, maybe 4. Number 6 here, I'm not even gonna do anything. It's already perfect. Wow, very nice. Maybe number 4. Oh, maybe. Oh. Sure, let's do number 4. Problem 111, number 4, and it is f of x 5x over, I believe it was this, I don't remember exactly. Yes, it is. Okay. 6 minus 2x. Okay. Now, at the very start, I just want to see things in a consistent way. And the way I always want to see it is descending powers of x. So the leading term here is negative 2x. They're just shuffling it around to confuse me. I will not fall for it. Multiple terms in the bottom. I see x's at the top. All bad. Long division has to happen. We will then do the long division. Inside the house is the numerator. Outside the house is the denominator, regardless of which one is simpler. Compare leading terms. 5x divided by negative 2x, negative 5 over 2. Negative 5 over, this is going to suck because of the fractions. Negative 5 over 2 times the whole thing is 5x by design, should be, and negative 15 that I take away. By design, the leading term should cancel. There's nothing else in the numerator, so I just have a 15. Oh, it's not that bad, actually. That's my remainder. Oh, nice. I'm now able to write quotient plus remainder over divisor. The denominator here doesn't look great, does it? I don't have a transformation to handle numbers in front of x other than 1. Now there are transformations, but they are really out of place here, and I don't need them because I can always simplify and take this other coefficient of x out of things by just taking it out and be left with x minus 3. And I'll put my eventual vertical shift at the end where it belongs. Then I simply need to merge the factor that I took out with the numerator, and then I can clearly see the transformation that will eventually give me the horizontal shift. So now my sequence of transformations is hopefully easier to spot. I'm going to start with 1 over x, my basic rational function. I only need 1. Then I like to do a reflection, so I multiply the right hand side by negative 1. Actually, yeah, it doesn't matter. Then You can maybe do the stretch by multiplying the right-hand side with 15 over 2 in this case. I'll go this way. Then I will replace x with x minus 3. I'll go this way. And lastly, the 1 I leave until the end. You can mix and match the others all you want. Leave the vertical shift to the end. My strong recommendation. If you want to avoid mistakes, at the very least, do that. And there we go. I know it doesn't look like the original function. I can't see both. But it is the original function. It's exactly the same. Doesn't look it. This first given version is definitely the simplified version, but as we saw with quadratic functions, the simplified version is very much not always going to show me the transformations. Yes, I can graph it. The better question is, can you graph it? I am not going to graph it because it is going to take time away from 5 other questions we could do. However, because of the fractions, right? However, I'll run you through the graphing. You start with your basic one, of course. Boom, boom, weep, weep. That's bad. Very bad example. Be more precise than that, at least. I was trying to be funny. Then we do a vertical reflection here. Then we stretch it vertically here. Then we shift it to the right by 3. There. Then we shift it down by 5 over 2. There. So definitely give it a shot. Just go really slow. As soon as there are fractions, anywhere, any topic, if there are fractions, just slow down. But there's still the basic transformations. That as long as you go slowly and try and be somewhat neat and careful, I don't believe there's anything here that we can't handle. But feel free, try this. Take a picture, send it to me. Let me check it. It's all good. But I need you to try it. And I need myself not to go crazy with a time-consuming graph when I want to do other things that I think are more productive for our session. Unless there are questions. I guess you did have a question. Can you graph it? But I want you to try it first. Tough love. You need to actually go through the motions. And if you can do it successfully, then you've got graphing. You don't have to worry about it. But it's good to actually do it. That and I'm lazy, let's be honest. Okay, I think that covers a good number of these. Some long division, good times. I want to do some, whoa, that was way too far. Scroll it back. There we go. I want to do some 112 questions and 113 questions, and that is the end. We are not this time going to talk about trigonometry, so no angles or the rest of that problem sections. Sometimes I include trigonometry depending on how our schedule goes. This time we won't get to it, unfortunately. And now it's a very sad time. I don't like how the page is flipping. Let me fix that. That's better. That's better. Okay. Okay, 112. Make a new page here. Oh, I already did. Haha. So efficient. Let's see what we got here. Let's at least do a polynomial one, right? Which one have we not done? I don't remember. We've done number 2. I'll do number 6. 112, number 6. Just to emphasize how we are going to look at these and that they're super simple. Polynomials are the simplest kind of function. And especially long-term behavior. Very, very simple. if I know what I'm doing and why. As x goes to negative infinity, then my function, which is x cubed minus 2x squared, tedious to jump back and forth, but I can't memorize the whole function, plus 3x will go to what? All I need to know is that long term, which is what this negative infinity represents, long term to the left, over here, the polynomial behaves like its leading term, which in this case is just x cubed. So for a very large negative number, what does x cubed do? Well, that's 3 of them multiplied together, so it's definitely going to be an infinity. And 3 negatives make a negative, so negative infinity. So all this is telling me is that when all the ups and downs are done, a couple of turns maybe for this one, I'm heading off to the bottom left, and I will never stop. That's all it tells me. And that's all I'm interested in sometimes. Long-term behavior. Polynomial, it behaves like its leading term, x cubed. It's not x cubed, just long-term. It behaves like that. It wants to be that graph, and it'll get closer and closer the further left I go. Okay. So now when I look at the long-term behavior of rational functions, all I need is the polynomial concept. Because rational functions are made of a couple of polynomials. Let's look at 11. Why not? Randomly selected. Problem 112, number 11. People take these things for granted, and then a month from now, I'm going to ask for the long-term behavior of a rational function, and then everyone just looks at me and with no reaction. But we did it, so that later on we can focus on actual new things. Everything I am saying in these early lectures, everything is there to help us later on. 2x minus 1 over negative 2x squared minus 5x plus 3. Don't know why I struggle to remember all of these terms. It's not that hard. All right. So now, maybe I'll write a little bit. As x gets really big, positive, yes, this behaves like 2x, leading term of the top polynomial, over negative 2x squared, leading term of the bottom polynomial. I can then simplify that. The 2's cancel. 1x cancels with the bottom x to get negative 1 over x. Oh, look at that. One transformation of a basic function that we have in our library. And therefore, I can go back and say, well, I know what negative 1 over x does. Let's look at 1 over x first. If x blows up in size, that shrinks down to 0. The negative has no effect because it's 0. And I'm done. So maybe let's make an arrow there. Once I look at that bottom, I go back and say, oh, 0. Now, if I think about this, I want to develop a sense of what rational functions are doing. And what they're doing is really having an interaction between two polynomials, the numerator and the denominator. Now, short term, a lot of crazy stuff can happen. I have no idea. I have to analyze this in a different way. But that's not the question. Long term, it's really a competition between the numerator and the denominator. Which polynomial is going to win? The one with the higher degree is eventually going to dominate the whole thing. And in this case, that higher degree polynomial sits in the bottom. So I'm going to create fractions in my y value with much larger denominator than numerator, causing the whole thing to shrink in size the further I go. The behavior is heading in a similar direction as a simple function that I can understand easily. What is that simple function in this case? -1/x. So what I do with this is I'm asking, I don't want to look at this function. It's unpleasant. Look at it. Ew. Can I look at something simpler that I understand, yet it behaves the same? I would rather look at that simpler function. If the behavior is the same, why bother? But the downside is I can only do that for these long-term behavior questions, unfortunately. Then eventually they behave the same. How far do I have to go for them to behave similar enough? I have no idea. Further than I can possibly imagine, and then a little more. All right. Hopefully that helps. We didn't do as many examples yesterday as we should, and I'll add these to our playlist for sure. What else do we have here? Do we have more? I have 16 minutes. I can do 2 more. They're fast. The slowest thing here is the copying. Let's see some variety. I want variety. Oh. Do I really have to make my own questions here? I'll do 16. 16's okay. Though the concept, once I have it, the concept's all the same, right? Oh, we've done 16, then not 16. I don't remember. It was yesterday. Who knows? I'll do 18, but I want to do something else. And I'm not seeing it. Fine, I'll do 15. It's the best one I have in this list. Not that there's anything wrong with 15. The others, I just want to see as much variety as I can. All right, what is the function there? Well, if x approaches what in this case? Infinity. Then I have a rational function, and it is x squared minus x minus 12. X squared minus x minus 12 over x squared plus x minus 6. X squared plus x minus 6 goes to what? Pretty sure I copied that right. And even if I didn't, who cares? 11. Did we do 11? I have a terrible memory. Oh, yeah, okay. Let's sort of visualize what we can here. I didn't do that. You're right. Well, we can't do much with certainty. But we can say, okay, we're going far to the right. We have a horizontal asymptote y equal to 0, which sits right on the x-axis. That's my 0 line. I do actually know. It's coming towards that line from the bottom because it's always negative, right? This negative, x is positive, so I have one negative in here. So right now, don't worry about how it approaches that line, just the fact that it does. Long term, it's heading closer and closer. It wants to be a horizontal line. And if I go far enough, it's going to be near indistinguishable from that straight line. All right. That's really all I can say. That's all this is trying to say. What happens in the middle, who knows? I don't. That's a question for another day, which we are going to answer, but we can't answer them all right now. But it's nice to visualize. What is this telling me graphically? It's nice. I like it. Okay, so now, long-term behavior. I don't really care if it's a positive or a negative infinity right now. In both of those cases, the rational function behaves like the ratio of its leading terms, which in this case happens to be exactly the same. They cancel each other to give me a 1, which is then the answer, 1. There aren't even any x's in there. So that means that the interaction between the two polynomials, long term, they match each other almost perfectly. One doesn't outgrow the other one, creating a fraction that blows up or shrinks or something. They match each other all the way. And when they get so big, these other terms that are technically different have almost no impact at all. They're so small in comparison to the x squared that you can't even measure them after a while, because there is no end to how big of an x value you're looking at. So I have a horizontal asymptote. This time we'll see it at least, so that's nice. It's the line, horizontal line y equals 1. Trying to make an axis here that's horizontal. Ooh, that's nice. That wasn't bad. So let's give it some space. Dotted line. It's just a guideline, really. Sitting at y equals 1. In this case, it's gonna be coming. Oh, I can't say how it's gonna come at it with confidence. We need some other tools to be sure. Yeah, I don't want to commit. It feels like guessing a little bit. Without having seen this before or having some other tools, which we'll have. We just don't have it yet. We'll have it in a month or so. We'll be able to easily pick how it's coming towards this line. But right now, I don't know. And I don't really care, to be honest. It's going towards this line somehow. That's good enough for now. Just separate that. All right, so don't worry about the fact that we don't know. People obsess, like, I need to know which arrow. No, you don't. Because even if I could, there's factors, I could probably figure it out. Later on, we're going to have tools that make it so easy it's not even an issue. So why would I spend energy on that now when that's not the question? Okay. All in time. All in time. So don't worry about that. Just finding the asymptotes first. I did say I was going to do 18, so I guess I should. I doubt you even need to draw it on a test at this stage. You just have to find the asymptote, or let's say it like this. You have to find the long-term behavior, and if that suggests a horizontal asymptote, then state that asymptote. The graphing is just to keep in mind visually which part of the graph are we getting information on. We're not going to graph a partial little piece of it right now. It's nice to see it for us, but it's not really something I'll test. It's just nice to visualize. Problem 112, number 18 is this one. Again, not hard. Let me just write it down. The most time-consuming thing here is copying down the question. Then, what's the polynomials involved? X squared minus x over 3 minus x. The long-term question is really the nicest question. I don't even care what happens to these. I care about leading terms. Everything else is completely irrelevant. So this behaves like, but it's a very important concept to introduce with this. Behavior is what we're looking at. If you say this equals x squared over negative x, that's wrong. It's not the same. It's not even close to the same function. But eventually, when all the messy detail in the middle is gone and done, they become closer and closer like each other. They'll never equal each other. If I now simplify this, I get negative x, right? So now I ask myself, well, I know how this behaves. It's a straight line. Y equals negative x. I'm going to have to use my straight line tool for this one. Actually, no, I don't. I need it to be a dotted line. Oh, man. It's close. Y equals negative x, it's there. When x approaches negative infinity, I'm going far to the left. That means in one way or another, I'm going up to infinity. Because I have a negative, I add another, I include another big negative number. Two negatives make a positive. The size of the number blows up. So graphically what's happening here one way or another is it's approaching this line. Now, I don't care about asymptotes if it's not a horizontal or a vertical line, but technically you do get other kinds of asymptotes. This one's called a slant or oblique asymptote. Doesn't actually matter for us, not our difficulty level. It's above our pay grade, but it does approach whatever the simplified behavior I look at. It approaches that graph, and I indicate that with a dotted line. Only eventually, though. Only eventually. In this case, the behavior was the same as this rational function, which when I flip it sits over here, right? So they sort of try and meet each other eventually. But we don't call, when it's a constant, we call the horizontal level that it's approaching the asymptote. All right. Good. It's good to see some more. Yeah. Let me just quickly, in our last 6 minutes, address that last problem, which isn't really new. Now, for the rational function, which these all are, we have said that horizontal asymptotes are determined. The horizontal asymptote question is answered in this way. What is happening far to the left, far to the right? That is the horizontal asymptote question. If you want to find a horizontal asymptote, you have to do this, period. There is no other way. For vertical asymptotes, it's where the y value blows up. And we saw for the function, the basic function y over 1 over x, which all these are built on in some way, it blows up as I approach 0, because then I'm going to get an undefined. So for a vertical asymptote, I'm looking for a denominator equaling 0, blowing up this whole y value. Where's my problem here? So, for example, we could do number 1. Number 1 is a perfectly good question. Problem 113, number 1. And there's not a lot of calculations and stuff that's involved. I simply have to state what are the asymptotes, if any. So the horizontal asymptote question is, if x approaches either infinity, then what happens to this rational function? Now, you don't have to do a whole thing. You just look at the leading terms. It's x over 3x, cancel the x's, 1/3. So, horizontal asymptote, silent p, y equals 1/3. Exactly the same thing we've done before. That's the only way to find a horizontal asymptote. That is what horizontal asymptote means. Is there stable long-term behavior? Okay. Vertical asymptote. Technically, it's where how is the simplest way to say this now? Let's say it here. When the y value approaches positive or negative infinity. Think of the basic rational function. Right? Are there x values for which this thing is going to blow up? And that is going to be caused by the denominator shrinking down to 0 and the numerator just being some other number. So this is going to happen if, in this case, x approaches 2, then y approaches some infinity. I'm not going to care which one now, because sometimes it depends on which direction I'm coming towards to. I don't care. It's blowing up in size either way. When that happens, we have a vertical asymptote, and it's the vertical line that sits at that x value. So technically, let me say it like this. For convenience, we're looking for when the denominator equals 0. But in our upcoming discussions, we'll soon see that we need to make sure that the y value actually blows up. Need to make sure that the y value actually blows up. And that will become more obvious as we go. We just need to give it some time. I'm just introducing the concept now, and we'll refine it and get better tools to handle it soon enough. Let me just scan over these real quick to see if I accidentally put that exception somewhere here. No, I don't think so. I think we're good. Let's look at number 9. If 3x minus 6 is heading to 0, well, the other way around. If x is going to 2, then 3x minus 6 is going to 0, and that causes the blow up in the y value size. So whatever value you put for x that will make the denominator 0, right now, yes, but technically, no. The y value needs to blow up. We're going to see it in the next few days. Just give me some time. Can't do everything at once. But for the most part, yes. For the most part, yes. Right now, you can think of it that way, and we're going to update that slightly in the next few lectures. So you're not really in trouble right now for thinking that, but it's not quite completely correct. It needs a little bit of a technicality that we need time for. It's not a huge technicality, so don't worry about it. So totally go ahead, think that now, but it's not completely finished, that concept. What do I want to do here? I want to do this last one. What is it? 9. I know I'm out of time. I don't really care. So I have my function x squared minus x minus 12 over x squared plus x minus 6. X squared plus x minus 6. All right. Horizontal asymptote question, always the same. I look at x approaching either infinity, and for the rational function, it actually doesn't even matter which infinity. The answer is always going to be the same. It's so convenient. Then I'm just going to say f of x approaches. I look at the leading terms. X squared over x squared, 1. So I have a horizontal asymptote, which is the horizontal line sitting at that y value, y equals 1. Vertical asymptote question, it's a little different. For that, I really need to see the polynomials factored. I need to see that bottom one especially, because I need to see which x values make that 0. Factoring that will show me, and I'll pick ones that I can factor fairly easily, right? Let's do the top one. Do I remember how to factor this? I'm asking you. That has to be a minus 4 and a plus 3, right? And the bottom one needs to be 3 and a 2 with a plus and, oh my goodness. Is that right? Plus and a minus. Oh, it's a good example. It's a great example, actually, that we'll elaborate on as we go. But right now, it's just good to see. Hopefully that factoring is right. I think so. Yeah, that's right. Okay, now, when you look at the denominator, I want to note something very important. So I'm going to answer your question about vertical asymptotes anyway right now. Note that if x approaches 2, then the y value does what? Is it blowing up in size? Well, yes, because close to x equal to 2, oops, I can run an arrow here. The function behaves like, remember, just behaves like something that approaches 2 minus 4, a piece that approaches 2 plus 3, a piece that approaches 2 plus 3 again, a piece that approaches 2 minus 2. I am not plugging it in and calculating it. Of course, we can't. It's all just behavior, and I can't really write it in any simpler way. So the first piece approaches negative 2. Okay, great, it's a number. The other piece approaches 5. The other bottom piece approaches 5 as well, and that is the problem guy, approaching 0, causing this whole y value to blow up to actually negative infinity. Well, yes, because I have one negative and all positives, right? That's actually not true either. Let's keep it as a choice. We'll figure out the choice later. I don't need to know the choice right now. So I'm just writing it like this. This is not a calculation. Infinity is not a number that this evaluates to. It's a behavior, hence my arrows. Okay. But by looking at the pieces, and that's going to become important later on as well, by looking at the individual factors involved and how they behave according to what x is doing, I can determine how the whole thing is going to behave. Now, if this is confusing for you, don't worry. We're going to spend a lot of time on this behavior question in the next chapter. It's just sort of setting the stage that, there's more happening here. But if I look at the behavior of each piece, then, oh, actually, it's not that bad. But now, if I look, okay, so vertical asymptote, certainly x equal to 2. If I look at what happens at x equal to going to 3, negative 3 rather, x approaching negative 3, then I'm just going to actually leave this open as a question because it leads directly into our next topic. What is y going to do? Well, y is going to behave like something that approaches negative 3 minus 4, something that approaches negative 3 plus 3, something that approaches negative 3 plus 3 again, something that approaches negative 3 minus 2. And you see, if I do it this way, I get a negative 7, or I don't get negative 7, I get something close to negative 7, something close to 0, something close to 0 again. I keep my brackets there as a help to remind me I'm not actually there. Something close to negative 5, and I see 0 over 0. Definitely error, but not quite infinity either. If I plug this in, they're both getting small, and they're both staying small. And I can see that more easily if I see all these are common factors I can cancel. X minus 4 over x minus 2. And the behavior of the function is actually the same as the behavior of this simpler function. Simpler function doesn't have these issues of dividing by 0. And they're always shrinking at the same speed, actually. And the other guys tell me what is happening overall. It's behaving like x minus 4 over x minus 2. And when I plug in that, I get negative 7 over negative 5 or 7 over 5. So it's not as simple, unfortunately, as just looking at where the denominator equals 0. If there's something in the numerator that matches that behavior by way of the exact same factor, then a cancellation occurs and the y value doesn't blow up. It's only when the denominator shrinks down to 0 and is not matched by the numerator, like when x goes to 2. Nothing at the top is shrinking down with that x minus 2. They're going off to, what did we say, negative 2 and 5. Well, that can't match what the 0 direction is doing. And the whole y value blows up. But there are other situations, and we have to then peek behind the curtain to see how we handle this, where if I have similar factors and behaviors on either side of the line, then they balance each other. And the behavior of the y value is still stable. And there's no vertical asymptote. So sadly, the situation is not that simple. As much as I want it to be, it's not. But it's also not really more complicated than this. We now have to develop a language or update our mathematical language to handle this behavior situation in a little bit more precise way. It feels a little hand wavy right now, and that can create confusion and lead me into trouble when things get more complicated. So how do I update my language to handle how functions behave so that I can analyze this with a little bit more confidence? That is exactly the topic for our next chapter. But that'll take us some time to really get into in the next few lectures. So it's a nice problem to see that things aren't quite as simple. Is there a way, a technique, a language update that makes this more precise and more calculation-like? Luckily there is, but we of course need more time to develop that. All right, any questions on this right now? We just need a little bit of patience, and we are elaborating on this very topic next. Other than that, we have reached the end. I apologize for going over, but it's very good to have that crossover.